All right, I'm recording and sharing screen now. So we started out talking about decibels and logarithms, just to get you acquainted with the decibel, because that's the unit that we use for gain. And I talked about linear scale versus logarithmic scale. That's why we use decibels. Talked about the front end of an op amp, which is a differential amplifier. We started to talk about operational amplifiers, op amps. We looked at all the ideal assumptions. So I just want to go over negative feedback. I just kind of hand wave. I drew those three topologies, which was an inverting amplifier, a non-inverting amplifier, and a voltage follower. I just drew them, and they all have negative feedback. They have a feedback loop. So open loop means there's no feedback. So what happens if an op amp is open loop? It's just going to try to amplify the signal to the maximum gain. So a 741 op amp has a gain of about 100,000. So if I put a 1-volt signal into it, it's going to try to amplify it to 100,000 volts, but it can't because of the voltage rails, the power supply on it can only go up to 15 volts or whatever the power supply is. It'll saturate when it gets to that point. There are some applications for, and we'll talk about it, a comparator is an example of an application of an open loop op amp. So we'll cover that later. So what is negative feedback? Negative feedback is when a closed loop system's output is fed back to the system's input. The output regulates, I should say, not the output, the feedback. I'm paraphrasing. Feedback regulates or counteracts the input. To stabilize the system. To maintain a homeostasis. If you Google this, they use that word homeostasis. It's kind of a biology term. They use it in terms of when your body is at homeostasis, all the hormones and your temperature, your body temperature, and blood sugar, and everything is all at like a stable level. It's used in biology. They use it in Google. Like if you Google what is negative feedback, that word comes up. So it's kind of like a self-regulating. In our case, the system, they use this word system. Our system is an op amp. It's an amplifier. It's an operational amplifier. So some examples of negative feedback. Here's a classic example, a thermostat. Oh, right there. So you set the temperature to 70 degrees. The furnace turns on. The room heats up. There's a sensor that goes back to the control that turns the furnace on. And the sensor, when it senses that it's 7 degrees, it turns the furnace off. Then when the temperature drops below 70, it turns it back on. That's a closed loop system. An open loop system would be if I turned it to 70 degrees, the furnace has no way to sense what the temperature in the room is. It'll just stay on. That's open loop. It's just going to stay on. It's just going to keep heating the room up indefinitely until you run over and turn the furnace off. Another example is a steam governor, a steam engine governor. So look at that real quick. Can everyone see this? Did anyone, have you ever seen this like in a movie, or it's these balls that hang down from this contraption and they spin, and they're like on like levers. What happens is centrifugal force makes them move out. So when the train is moving faster, the steam engine train, the balls move out from centrifugal force because this thing is spinning. And then what it does is it cuts the steam to the engine. It controls the valve, so then it slows down. And then when it gets to a certain point, then it lets more steam in and it goes back out. It's another example. Cruise control on your car. You set the cruise control at 70 miles an hour, you're on the interstate, and you set it. You start going up a hill, your car is going to slow down. So then the computer in your car is going to tell it accelerator is going to increase the accelerator so that you'll speed up so you stay going 70. Then you start going down a hill, let's say. Now you start speeding up and you're going faster than 70 because you're going down a hill. So then it'll back off the accelerator. That's a closed loop system. So what's the opposite of negative feedback? Positive feedback. Positive feedback is used in electronics sometimes for oscillators, but it's bad for amplifiers because the amplifier will become unstable. What's an example of positive feedback? I saw some in there, and there were a lot of them. There were biology and anatomy and stuff like blood clotting and stuff like that. I thought of one. Here's an example of positive feedback. It gets cold, like in November, December, it gets cold. It snows. The ground's covered with snow. So the ground is white. So the white reflects sunlight, and then it gets colder, and then it snows more. You see it's reinforcing itself. It's a positive feedback loop. It's actually a complex chaotic system. And I'm oversimplifying it, but you kind of get the idea. It keeps the system keeps feeding on itself. So basically what happens is the feedback loop is reinforcing something changed by the input. You change something a little bit, and then you get a feedback, and it says change it more, and then it runs away, and it just keeps going more and more and more. So you can think of it like this. Here's the system. You have an input, an output. This is a feedback loop. And like I said, you can think of this as a thermostat setting. Some voltage. Speed setting. So let's talk about Talk about voltage controlled voltage source. Here, let's go to another page. Maybe that'll fix my problem. No, it doesn't. There. So there's 4 types of negative feedback. What's going on here? Here, let's do this. I don't know what I did. I must have bumped something on the tablet. No. That should be good. This is taken right out of the textbook. There's a voltage controlled voltage source, a current controlled voltage source, a voltage controlled current source, a current controlled current source. This is the one that we studied. Can anyone think of an example of a current controlled voltage source? Voltage control voltage source. Remember yesterday I drew that BJT amplifier? So you put some current into the base, you get some current through the collector, and the output is a manifestation of the current flowing through that resistor, through the collector resistor. Remember I drew this? Put some current into the base. You get current through the collector. That's your output. Here's your input. Current controlled voltage source. This is what we study, voltage controlled voltage source. So here's our 2-port model. This is an ideal, there's a 2-port model. This is an ideal DCVS. Two ports, input, output. V in, V out. We have high input impedance and low output, low Z out. For what we're dealing with, sometimes you'll hear me say input impedance, output impedance. Impedance is everything. Resistance, inductive reactance, capacitive reactance, it's everything. That's what impedance is. For what we're dealing with, it's input resistance, output resistance. We're dealing with an op amp. There's no inductors. At high frequencies, everything is an inductor, a capacitor, and a resistor at very high frequencies. At high frequencies, there's no such thing as a resistor. It's actually this at high frequencies. We're not dealing with real high frequencies. So our operational amplifier, that chip I showed you, that 8-pin chip, it's just resistance, input resistance, output resistance. This is our output. This, it's not infinite. Ideally, it's infinite. It's not infinite, but it's high. And for our 741, it was about 100,000. And then this would be a stiff voltage source. Again, this is low, but not zero. And this is basically this VZ, I'm just going to call it a VCVS. It's a mirror image of our op amp, our ideal op amp. It's the same thing. And again, I'll ask the question again. Why do we want, or why, I should say, why is it ideal to have this high? So if this is a real small signal, if this is low, it's going to draw current from my signal. I want my whole voltage signal to be here. I want all of it to be here. So ideally, if that's open, the whole signal is there. None of it gets wasted or dissipated across this input. It's a series circuit. What about the output? Why is this ideally low? If it's high, part of my output, it's dropped across here. We talk about this in advanced circuits. It's called maximum power transfer. Ideally, maximum power is transferred to the output when this load resistance is equal to this internal, I should call that RS, series resistance, maximum power. And this is a theorem. I'm not going to go into that. That's in advanced circuits. And again, if you think about it, it's a series circuit. Some of the voltage is going to get dropped across here, and some is going to get dropped across here. The bigger this is, the less you get out here. It's just two resistors. I mean, if you want, you can draw it like this. I mean, if it makes more sense, draw it like this. RS, RL. If this resistor is bigger than this one, V source, we'll say 10 volts, more of this voltage is going to get dropped across here, and less will be dropped across here. So you want this to be low. And with an op amp, it is low. So I have a development that I got out of the textbook. I'm gonna go through it. And let's go to another page. Does everyone have this page? Because it's gonna be gone in a minute here. So our non-inverting op amp. This is an implementation of a VCVS. And what did we say yesterday? A equals 1 divided by R. I want to make sure I write the same, write it. I use the same variables. R2 and R1. Sorry. Okay, this is the formula that I wrote down yesterday. I didn't develop it, I just wrote it down. I just gave it to you. Okay, now I'm gonna use the term or the variables that the author uses. So I'll draw our circuit over here. The author uses RF and R1. Here's our feedback path. So part of the output voltage, which is voltage across R1, is placed on the negative terminal. This is RF. Yeah, in R, when I drew this yesterday, we talked about this yesterday. I used R1 and R2. I'm just using the same. So this was R2 yesterday. I'm using, in case you want to look at the textbook, I don't want to start mixing up component reference designators and mixing them up because then it'll be confusing if you look at the textbook. This is what they use in the textbook. So AOL is A open loop. So I'm going to say it's about 100,000 or greater. Okay, so here's what the development in the textbook. They assign this letter B and they call it V2 over V out. And this letter B is the feedback fraction. Or the feedback attenuation factor. And this is given, and I have yet to find where they got this, but I'll figure it out. This right here is loop gain. So closed loop gain equals open loop gain divided by 1 plus loop gain. Loop gain is AVOL times B. So this is gain of feedback path. The larger, the better. And this gain, or this stabilizes voltage gain. And I have a quote in my notes, and I don't know why. It's maybe because the stabilize came up. My professor at MSOE for op amp design, he said, Dr. Holland, he said, an unstable amplifier becomes an oscillator. An unstable oscillator becomes an amplifier. I don't know if he made that up or if someone else said that and he just repeated it, but so this system right here is unstable without a feedback loop. If it's open loop, it's unstable. So if you have a time changing input in your open loop, the output could oscillate. It's no longer an amplifier, it's going to start oscillating. Okay, so I'm gonna erase some stuff so I can continue this development without, because I want to stay on this page. Can I erase all of this? Does everyone have that? I'm gonna erase it. So for a VCVS to work well, AV open loop B must be much greater than 1. So here's our formula, AVOL. Now I remember where this came from. If this is much greater than 1, can I just say AVOL divided by AVOLB? So let's do this instead of equals. I'm going to use the about equal to. Is that fair enough? If this right here is much, much, much greater than 1, it swamps out that 1. So I can just throw that 1 away. And what does this equal? It equals 1 over B. Because right? AVOL cancels and you got 1 over B. We set up here that B equals V2 over V out, which equals RF divided by R1 plus RF. This is voltage divider. Look at RF divided by R1 plus RF. AV is approximately 1 over B, which is 1 divided by, oh, I'm sorry. I thought that looked wrong. This is R1. Sorry. Do you see where I made a mistake here? This voltage here is R1 divided by both of these. It's a voltage divider. Remember it? Well, I talked about this. I reviewed this in advanced circuits. I didn't review it in here, but you should know what the voltage divider rule is from DCAC1 and DCAC2. Voltage divider. Here's my aside.
V2 voltage drop across the R1.
Yeah, it's a voltage divider. There's this voltage. V2 is R1 divided by the sum of the two. So let's look at this. What's the voltage across here? Let's do this. What's the voltage here? We'll call it V2. V2 is V1 times R1 divided by R1 plus R2. V2 over V1 equals R1 over R1 plus R2. Do you see it now? I don't want you to think I'm hand waving this. I'll admit I'm hand waving this. I got this out of the textbook. And this is just some arbitrary constant or an arbitrary variable that they're assigning to this ratio, V2 over VO. V2, VO. So what I'm going to do is substitute for B, 1 over B. AV is 1 divided by B, 1 divided by all this. What does that equal to? If I want to put this upstairs, this is a compound fraction. If I want to move this upstairs, I just flip it around. Right? If I want to split up this fraction, I can go say R1 over R1 plus RF over R1. Is that fair enough? What does that equal? That equals 1 plus RF over R1. So that's just a development. It's a different way to develop that gain formula. Reasoning your way through, and you can look at it in the textbook if you want. At the end of the day, you need to know this formula right here. And on a test, you can write it on your note sheet. Remember, this is a non-inverting amplifier. What was an inverting amplifier? Oh, does anyone remember? So let's do an example and then we'll take a break for 10 minutes and then I'll come back and talk about half PowerPoint frequency response and then we'll do lab 2. So here's an example. Everyone have this? I used to hate when they drew it this way, but I actually like it now because it's easier to understand the circuit. Because you can draw this differently. You can draw this so that so this loop goes over this way and the resistors like up here. I think this I do like it this way. At first I didn't, but now I do. So we said B is R1 over R1 plus RF. So that's 100 divided by 100 plus 3.9K. And that's 0.025. AV is 1 divided by B, which is 1 divided by 0.025, which is 40. If you plug these values into the other formula, I'll make it in blue. If you plug these values into this formula, you should end up with 40. This is basically just saying the same thing. It's two ways of saying the same thing. Again, like I said before, this is the formula you care about. And like I said, this might be R2 and R1. This might be RF and RI. Every textbook you look at, they use different reference designators for those resistors. I mean, it's nice to have RF because you know it's the feedback resistor, but it's also could be confusing. As long as you know which one the feedback resistor is. So is there any questions? We can take a break and then I'll talk about this and we'll do lab 2. I knew I had time. I don't see you over there because you're behind the monitor, so. All right, so I'm gonna pause this and take a break. I'm recording now. All right, so what I have here is about a half hour or so. What I have left to talk about. Maybe a little longer, and then you can work on your labs, take a break, work on your labs. So let's go to another page. So let's draw our magnitude response. There's frequency, here's gain. Here's our low pass filter. Kind of goes like this. Right here, there's 0 dB. Right here, it's minus 3 dB. There's FC. And what did we call it? We called this point the break frequency, the corner frequency. We had all these names that we called it, and they all mean the same thing. Cutoff frequency. Half power point. And 3 dB down point. So the question is, why is it called the half power point? Remember, this is the response, the frequency response of a filter, a passive filter, or it could be an active filter. And this is in the frequency domain. The vertical axis is gain. So right here, it's just passing the signal. And right here, the signal is getting cut off, and then it drops off. And I can unequivocally state that V out does not equal half of V in. So why not? And I think what I told you was, said it's 0.707. So let's draw the circuit right here. So that that minus J, we learn about the J operator in advanced circuits. We're not going to talk about it in this class, but it just means negative 90 degrees. That's all it means. I mean, everyone, you should have learned about in DCAC 2, you should have learned about reactance. And you should have learned that the angle of inductive reactance is plus 90 degrees and the angle of capacitive reactance is minus 90 degrees. So that's just notation. So would it be fair enough to say that B out is VC divided by VR plus VC? Right here, this voltage is this voltage divided by this voltage plus this voltage divider. Remember that this is not a scalar, it's a phasor. Again, if you're in advanced circuits, you'll get this background. I'm just giving this is just a proof or derivation. A phasor is just a complex number. There's a magnitude and an angle. Again, you should have learned that in DCAC 2. So would it be fair enough to say that we can draw this graphically? Our resultant vector, or it's like a vector, but our resultant phasor is VR plus VC. Here's our angle. This is 90 degrees here. This is a geometric proof of this. Would it be fair to say that I know this angle is 45 degrees because I know VR and VC are equal? Remember I said it's the half power point. Half power point. Half the voltage is across here. And half the voltage is across here. So VR equals VC. Remember from geometry, you draw a right triangle. If the sides of the triangle are equal, the angle is 45 degrees. All the angles add up to 360. Or 180, I'm sorry, 180. So you got 90 plus 45 plus 45. So angle theta is 45 degrees. So we could use a proof from an identity. Oh, and here's another thing. Let me go off over here for a second. When you did that frequency response sweep, that AC sweep in multisim, yep, Tuesday, you did lab 1 Tuesday, right? You remember underneath that Bode plot, that magnitude response, there was a phase response. Here's our phase response. Now, damn it. At cutoff, the output is shifted by 45 degrees. We don't spend a lot of time talking about this. We'll talk about it in advanced circuits. I just wanted to just put that out there so you know what that means. Because this is a reactive component, the phase changes. The phase angle changes as the frequency changes. All right, so let's use a proof from an identity proof. Let's just say, for instance, that BR equals VC equals 1 volt. Oh, another way we can find this angle. If this is 1 and this is 1, can we use trig? The arctangent of theta equals 1 divided by 1. SOHCAHTOA. Everyone remembers SOHCAHTOA? Did everyone hear that? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. If you put that in your calculator, the arctangent of 1 is 45 degrees. So that's another way that you prove it. That you can get this. So let's use some more trig. We could say the sine of theta is opposite over hypotenuse. Sine of 45 degrees is 1 over 2. Remember I said VR, this. 1 plus 1 is 2. If you put this in your calculator, the sine of 45 degrees, wait a minute, sorry. Let's just leave this. Sine of 45 degrees, 0.707. So VR plus VC is 1.414. So V out is 1 divided by 1.414, which equals 0.707 at half power. That's where this came from. So one more thing, another way to look at this, one more thing. Can I erase this phase plot? Does everyone have it? Remember I called this the 3 dB down point? We had this big list of all these names that the same, it all refers to the same thing. Well, let's do the same identity proof. We know that AVDB is 20 log. Again, we talked about this on Tuesday. This is a formula for decibels, V out over VN. So let's say our input is 1. Let's solve for V out and see what we get. What do you think we're going to get if you had to guess? VN is 1 volt at -3 decibels. Let's say this is, remember, this is a way to express voltage gain. But let's say our input was 1 volt. This is our output right here. So let's just do it. Let's solve the equation. So we know -3 dB. We're trying to solve for V out. We're solving for this. So we know VN is 1 volt. So the log of V out so this is minus 0.15 is log of V out. So what does that mean? That means that V out is 10 raised to the negative 0.15. Remember, that's the law of logs. I shouldn't say it's the law of logs. It's what a logarithm is. This, a log of some number equals an exponent. This is the exponent on base 10. If you don't write the base in there, you assume that it's 10. Put that in your calculator. On this TI-89, I don't know any easy way to put log. So you have to go alpha L, alpha O, alpha G, parenthesis. And wait a minute, I don't have to do that. I can just say 10 raised to the negative 0.15. So if you put that in your calculator, what do you get? .707. That's why the half power point isn't half of the input power. All right, you can work on that. That's all I have for lecturing. You can work on the lab. I'm gonna stop recording. I'm gonna take a break for about 5 minutes, and then if you need help with the lab, I can do it on the, I'll do it on the overhead. I'll show you how to do the calculations. So we're gonna stop this.